All right, so our next portion of exploring our magnetic fields involves magnetic forces on moving charges. So in this case, we're going to look specifically at individual charged particles moving in a magnetic field. So a charged particle will experience a force anytime it is moving in a magnetic field. So remember, B is our magnetic field vector. V is now the velocity of the particle. Q is the charge of the particle. And F is our magnetic force. Now, this is a cross product. Right here, sorry, a little delay there. So a cross product is a mathematical operator that finds the components of a vector that are perpendicular to each other. So vector products are kind of outside the range of the course, but to understand why this works the way it is, we have to understand a little bit about the cross product. So, for example, if my magnetic field B was to the right and my velocity V was north, they're at 90 degrees to each other. If I take V cross B, I just get V times B. If B and V were parallel to each other, then V cross B would be 0. So we're looking for the components, essentially, that are perpendicular to each other. So if they're not at a 90-degree angle to each other, if they're at some other angle theta, only the components that are perpendicular to each other will actually contribute to the magnetic force. This was kind of like torque in mechanics. Your lever arm R had to be perpendicular to the force in order to create rotation. So what you would do is you would make some sort of triangle, and you would find the component of B that was perpendicular to V. So our cross product, V cross B, can be simplified, as long as we're in 2 dimensions like we have here, into VB sine of the angle theta, because I could see that B perpendicular here would be the opposite side of that triangle, which would cause our product to be based on sine to find those components. So this does simplify down in 2 dimensions into VB sine theta. So you can rewrite this for our purposes as QVB sine theta. But this idea of them being 90 degrees and the fact it's a cross product is going to affect the direction, which we'll talk about in a little bit. So F is the force on the particle, V is the velocity of the particle, and the magnetic field vector is B. And of course, Q is the charge. Not sure why that's not labeled right there. So Q is our charge. So what is the force if the charged particle is at rest? Well, there is none. So if our velocity was equal to 0, then our force would equal 0. So magnetic fields exert forces on charged particles as long as the charged particle is moving. If the charged particle was at rest, it would not experience a force. And that does come down to the fact that it's the motion of the charged particle which is creating the magnetic field. And so if our particles are not moving, then they're not magnets. So therefore they wouldn't be affected by a magnetic field. So the force is proportional to Q, including the sine of Q. So remember that the sign, whether it's positive or negative, negative is basically going to mean opposite. So you're going to get the same magnitude of force, but the direction of the force will be exactly opposite if you have a negative charge versus a positive charge. The force is proportional to the magnetic field B, so if you double the magnetic field, you're going to double the force, double the charge, double the force. It's proportional to V, double the velocity, double the force. And then when B and V are parallel, the force is 0. Vanishes means go to 0. When B and V are not parallel, the force is perpendicular to both of the original vectors in terms of direction, and we can use that sine theta in the product to find the magnitude. So our 2D cross product is QVB sine theta. We don't have our arrow on top of our force. That's why the absolute value is here. This is just to find the magnitude of the force. So you could find either the component of V that's perpendicular to B or the component of B that's perpendicular to V. Either one of those true. You have to be careful when using this version with the sine theta. In order to use that, that has to be the actual angle in between. Sometimes they'll give you like V's going this way and they'll tell you that B is going that way, and they give you like that angle. If they give you an angle like that, that's not the angle between B and V, and if you tried to use the sine theta with that angle, you would not necessarily get the right answer every time. And I would have found the components of B. So there'd be a component of B here that is parallel to V, and then going up there'd be a component of B here that is perpendicular to V. So there's a 90-degree angle right there. So I would have actually found that component that's perpendicular and multiplied it by V if I wasn't sure if I was using the correct angle theta. So we have to be careful here because what's actually going on with this cross product and what it's calculating, for example here, if we wanted to find F is equal to QV perpendicular times B, we would find that perpendicular component right there. So we'd be multiplying those products together. And you could do it the other way, like I said. Instead, you could do V times B perpendicular. In that case, you're finding the component of B that's perpendicular, so that would be your 90-degree angle. So two different ways to go about looking at that. Now, where does the force vector point? Well, the force vector is going to be found using a right-hand rule. There are different right-hand rules. I use the right-hand rule that goes, oh my gosh, that goes for any cross product. So if you're, you might not have seen a right-hand rule for a cross product because this is an algebra-based course. So this might be completely new to you. But if you look up right-hand rules, there are a whole bunch of them for electromagnetism. Magnetism in particular has a lot. We're going to do a lot of those right-hand rules. I use the rule that works for any cross product. It's not the same rule that you're going to see everywhere. If you find something online and you like it better, go for it. You want to find something that makes sense for you. This is just the way that I was taught it. I was taught a way that uses the fewest number of rules you have to memorize. Okay, so knowing that this is a cross product is going to help us out. So if you have any cross products, and I've got a video about this that's linked so you can see more, but you ignore the Q except for the charge, like the sign, whether it's positive or negative. You work on the cross product first. So that's this part right here. What you do is whichever vector in the cross product is listed first, which is this one, this is where your fingers go. So in this case, your fingers point in the direction of V. So here we've got V is going to the right. So you can see that their fingers were initially pointed towards the right. And then you rotate your palm. So it is, that doesn't say palm. You rotate your palm so that it is facing B. So if I point my fingers to the right and rotate my palm is up. My fingers were to the right. So if you can kind of do that. So if I take my right hand, it's a right hand rule. So you have to use your right hand. And I point my fingers to the right, and then I rotate my palm so it's face up. Then what happens is where my thumb points is going to be perpendicular to all of those. and that is where my thumb points, is in the direction of F. So F is where the thumb points. Like I said, I have a video of me actually with my hand moving it, so you'll be able to see it better. It's kind of hard to do it just here in the voiceover. So this rule is for a positively charged particle. If you have a negatively charged particle, negative means opposite. So you could do the right hand rule as it is written, and then just flip the direction of F. So in this case, F points towards the bottom of the page. So if this was a negatively charged particle that was moving, F would point towards the top of the page. Or you just use your left hand. If it's a negative charge, you use your left hand. Okay, and that will have the same result of flipping your force in the opposite direction. So please watch my video that actually has the hand rule examples where you can actually see my hand. That will help. So we want to practice this together and make sure that you can do this. So what I would do is look at each of these and go through and try and make sure that you can match the 4 examples. So in this first one right here, picture that V is going straight towards the top of the page and B is pointing towards the right. So that's a negative charge. This first one is a negative charge. So start with your left hand, point your fingers towards the top of your screen. Keep your hands straight and your fingers flex out as straight as they can go. Very pointy. And then rotate your palm towards the right of the page because B is pointing towards the right. When I do that, I can see that my thumb is pointing out, which is kind of what this is showing. So you do your V towards the top, B towards the right, and then that force would point out of the page. Now on this one right here, it's a positive charge. So same idea. You point your fingers towards the top of the page, top of the screen. That is your V. You rotate your palm so that it's pointing towards the right. This forces my thumb for me to go into the page. Okay. So instead of out of the page, it's going into the page. So this one is kind of showing your Z-axis is here. I hate forced perspectives. Your Y-axis is here, and then your X-axis. That's positive X, positive Y, positive Z is how this is showing it. So Z is like in and out of the page. X is left and right. Y is top of the page and the bottom of the page. And Z is in and out of the page. That can kind of help in these perspectives. So on this one, I would picture that the page, this is the page right here is on your desk. Picture that one where the page is like laying flat on your desk. So V is pointing directly to the right. B is kind of pointing towards the top and right of your page. So if I point my fingers on my right hand, because this is a positive charge, to the right, and I rotate my palm towards the top of the page, because it's towards the top there, my thumb is going to point straight out of the page. Okay, that's the positive Z direction, out of the page for that force. Same vectors, but if it's a negative charge, I either flip it and go from positive to negative, so my force flips directions with that negative charge, or I use my left hand. I would still point my fingers directly to the right. I'd rotate my palm so it faces that B vector, which is towards the top of the page, and my thumb would point into the page in that case. So now try this one. In this case, your V and B have switched, and we have a negative charge. So try it, pause the video, try it yourself, come up with it, and then resume. So if I was to do this one, because it's a negative charge, I'm going to use my left hand. And that V is kind of going at an angle, so it's going top and right. So picture pointing your finger towards the top and right of your page. B is now towards the bottom of the page. So I'm going to rotate my hand to point the bottom. This is going to cause my thumb to point straight out of the page. So that's going to come straight up out of the page. That's going to be in the positive Z direction. So if we were to look at the magnetic field units from this equation, if you rearrange to solve for B, we know that the unit for the magnetic field is the Tesla. And we said that a Tesla was a kilogram per coulomb times second in our previous video. But that's also the same thing as a Newton per coulomb times meter per second, because a Newton is a kilogram meter per second squared. So if we divide by coulombs times meter per second, what ends up happening is meters cancels, and one of the seconds cancels. So on the top you get kilograms per second divided by coulombs, so then you just move the per second down to the bottom. So that's going to give you another way to show that if we use this equation, we still get units of Teslas. So now, what happens when we do put a charged particle into a uniform magnetic field? Remember, uniform means constant in magnitude and direction. So we're going to do an example of an electron traveling at 2 times 10 to the 7th meters per second in a plane perpendicular to a 0.01 Tesla magnetic field. Our goal is to describe the path. So we're going to start with a diagram. We're going to have to start with a lot of diagrams here. It's a lot easier to see it once you have the diagram. So here is our diagram. We're going to assume that that electron is traveling in the negative y direction at that instant. Our magnetic field B is pointing out of the page. That's what those dots represent, is it's pointing out of the page. So we are going to use our force is equal to QV cross B. So we're going to use our right hand rule for that. So V is going to be where my fingers point. So I'm going to take my left hand, because this is a negative particle, and I'm going to point my fingers towards the bottom of the screen. So put those straight down. And then I have to rotate my palm so that it faces B. So magnetic field is out of the page. So if I point my fingers on my left hand straight down and rotate my palm up, that forces my thumb directly to the right. So my magnetic force is directly to the right. That's where my thumb points. Once again, watch that video that's posted that has my hand showing the different motions. I think that will help. So if you do that, notice that the magnetic force and the velocity are perpendicular to each other. So we know what direction the force points at that instant, but because they're perpendicular to each other, we're going to start to curve. And so what ends up happening is we get circular motion. As long as we assume that our charged particle stays in that field. I know the diagram doesn't show it staying in, but it's going to move in circular motion. And it's going to be uniform circular motion, kind of pulling back in from Physics 1401. It's uniform because our force is based on QVB, the QVB sine theta. But because our magnetic field and our velocity are perpendicular to each other, because one's in the y direction, one's in the z direction, our sine theta goes away. So this is just going to be QVB. Oh, not 1. Sorry. It's equal to 1. It's not 0, it's 1. Our sine theta would actually be 1. Sine of 90 is 1. So we would get QVB. So Q is constant because that's the charge of our particle. V is constant. And B is going to be constant, okay, at that first instant. Now, we know that with circular motion that our force can only change our speed if there's some component that's parallel. If our force and velocity are perpendicular to each other, the force changes the direction, but not the magnitude of the velocity. So we're going to move in a circle at a constant speed. And we can see that if we look at other points, so we look at when our negative particle is here, our velocity is going to be tangent to the circle, so it's going to be moving to the right. Our force is going to be moving towards the top. So our force always points towards the center of the circle. You can check that with your right hand rule. So this is uniform circular motion. It doesn't go away when you leave Physics 1401. So since our acceleration is in the radial, so centripetal, not tangential, there's no change in the magnitude of the velocity, but the direction does change. So our magnitude is constant, but our direction changes. So this will move with a constant speed in a circle. The acceleration would be centripetal acceleration, which is equal to v squared over r, where r is the radius of the circle that is being made. So how do we find the radius of that path? So we know that it's a circle. We know which direction it goes around the circle. How do we find the radius? So we just said that our magnetic force is acting as the centripetal force. So our magnetic force FB is equal to our centripetal force. Remember, our centripetal force is a net force, so it's equal to MAC. And our magnetic force is QVB because our cross product V cross B is just equal to VB because it's perpendicular. So that's nice. So what ends up happening is one of the V's cancels out here. So that's going to simplify our math down a little bit. So perpendicular QB cross B is QVB. And if you solve for R, we get R is equal to MV over QB. So this MV is momentum, P. That's our momentum of our particle. So if our mass is higher or our velocity is higher, we are going to get a larger radius circle. I think that just kind of makes sense. If our charge is larger or our magnetic field is larger, our radius is smaller. So basically, the stronger the charge and the stronger the magnetic field, the tighter that circle is going to be. The better the magnetic field is going to be at pulling it in. All right, so this is going to be a little different situation. We have the magnetic field of the Earth at a certain location is directed vertically downward. In this case, because we're talking about the Earth, when we mean downward, we mean it's pointing into the ground. So we're pointing towards the ground. It has a magnitude of 50.0 microteslas, because we saw that earlier. A proton is moving horizontally towards the west, and it's a proton. So when I'm solving problems, I try and, like, in my brain, circle the charge so that I know which right-hand rule I'm using, positive or negative, because they're in opposite directions. And it gives us a speed of 6.20 times 10 to the 6 meters per second. We want to know what are the direction and magnitude of the magnetic force, and what is the radius of the circular arc followed by this proton. So I start by drawing a picture. So I have north, south, east, and west here. So I'm going to assume that my positive charge is moving towards the west. And it gives us a speed v of 6.20 times 10 to the 6 meters per second. Now, it tells us that our magnetic field is downward. Like I said, we're saying towards the ground. So in this case, if I'm doing north, south, east, west, that's going to be into the page. So my magnetic field B at that location is into the page and has a value of 50.0 microteslas. So we want to know what the direction and magnitude of the magnetic force the field exerts on this charge. So our cross product is QV cross B, which is really just going to be, we could do it as QVB sine theta. But since into the page and west are going to be at 90 degrees to each other, our sine theta is just equal to 1. Or, since you know that V and B are perpendicular to each other, our V cross B is just VB. So however you get there is up to you, whatever you like better. So, but our force is going to be QVB. So our proton is an elementary charge. So it has a charge of 1.6 times 10 to the negative 19 coulombs. Our speed, V, is going to be 6.20 times 10 to the 6 meters per second. And our magnetic field B is 50 microteslas, which is going to be 50.0 times 10 to the negative 6 Teslas. Micro is times 10 to the negative 6. So if you were to plug that in, you should get a magnitude, I put it down here, of 4.96 times 10 to the negative 17th Newton. So that's a very, very, very small force. So what direction is that going to be? So once again, if we use the right hand rule, I'm going to point my fingers in the direction of my positive charge. This is my right hand. My palm goes in the direction of B, and then my thumb is going to be where the force is located. So with my right hand, if I point my fingers to the west, that's left on my page. My palm needs to go into the screen or into the paper, so that makes my thumb go straight down. In this case, straight down the page is south. So towards the bottom of the page is south. So that is going to be south, which we can check right there. So then we want to know what radius of the circular arc is followed by this. I'm going to add that 4.96 times 10 to the negative 17 newtons. So I'm going to go through, hold on, pause this for a sec, and assume that I've not memorized any formulas. So if I were to look on my formula sheet, I know that I have my centripetal force equation is on there, if you look at that for mechanics. So my magnetic force is equal to my centripetal force. My centripetal force, because it's a net force, is equal to MAC. So my magnetic force is going to equal to be mv squared over r, because my centripetal acceleration or my radial acceleration is v squared over r. So I could then solve for r. Like I said, I'm doing this one just as if I had just found my force. So I'm going to multiply r on both sides. R's cancel. So I get r times FB is equal to mv squared. And then I divide both sides by FB. So we get r is equal to mv squared over FB. So I could plug in my mass of my proton, which if you look up is 1.67 times 10 to the negative 27th kilograms. That's on your formula sheet. Times our speed of 6.20 times 10 to the 6 meters per second. Squared, don't forget that square. And then our magnetic force was 4.96 times 10 to the negative 17th newtons. And that should give us an R that rounds somewhere around there to about 1.29 times 10 to the third meters, which is 1.29 kilometers there. Now, if you had memorized the equation or wanted to go back and solve this the way we did before, so we could have gone back here. Let me pause for a sec. And since our force was equal to our centripetal force, I could do the QVB is equal to the mv squared over r. You could have canceled the v's out. QB is equal to mv over r. You would have then multiplied both sides by r. So you get RQB equals mv. And then you could have divided both sides by QB. And you would get that your R is equal to mv over QB. So you could have skipped the force part and then just done your mv over QB and solve for your radius that way. So if we have this proton and it is in that field, it is going to be moving in a circle with a constant radius. The velocity is always going to be tangent to the path. The magnetic force is always going to point towards the center. So your magnetic force is changing directions. Your velocity is changing directions, which is why there is an acceleration. And our force isn't technically constant because it is changing directions. It's constant in magnitude, but not direction. But it does always point radially towards the center of the circle. So you could use this equation to solve for r. You could use this to solve for the speed that it needs to go at a particular radius. That's one way they might ask you to solve a problem. They could also ask you for other things. They could ask you for the period. Because this is circular motion, our speed is distance over time. So for one trip around the circle, that distance is going to be 2 pi r. Our time is going to be the period t. So if you rearrange that and solve for t, that gives you 2 pi r over v. If you sub in for r, you could actually find that speed in terms of the mass, the charge, and b, or just find r. But that's something they can ask you for, is the period that it takes, the time it takes to go once around the circle. They could also ask you for the frequency. Sometimes they call this the cyclotron frequency. A cyclotron is a physics apparatus in which you have charged particles that are accelerated around circles. They're used for research and all sorts of other things. And frequency is just 1 over the period. So if you can find the period, you can also find the frequency. So different types of things they could ask for. Now, that was if your velocity and your magnetic field are perpendicular. If any component is not perpendicular, so for example, I have an initial velocity in this example that is at an angle. So there is both a parallel and a perpendicular component of that velocity here at the start. Then what's going to happen is that the magnetic field cannot affect the parallel because it's based on the cross product. Magnetic fields only affect the perpendicular components of the velocity, and it just causes you to change directions, not speeds. So V parallel remains constant, but V perpendicular rotates through a circular motion. So this is going to create a helical motion. It'll form a helical. So if I go through, we can see, woo, that you would get this charged particle moving through a helix shape. I won't put any of those on a test for you, but they're kind of fun and interesting. The important thing is the magnetic field only affects that perpendicular component of the velocity. So that vertical component stays the same. So instead of going in a circle, it goes in this helical coil. Now, why is this kind of fun and important? Is this helical motion does all sorts of cool things. So there's something called a magnetic bottle, which is made by having 2 current carrying loops around. And we'll see that current carrying wires create magnetic fields. And so these are actually creating magnetic fields that are in the same direction, but because they're created here, then the fields are going to get weaker the further away they are. The field is actually weaker in the center. And what's kind of fun is this actually creates kind of like a trapped effect, and this charged particle ends up either being forced, if it's on this side, it's forced to the right. If it's on this side, it's forced to the left. So it actually traps that charged particle, and it cannot escape this magnetic field on its own. It's kind of cool. Another cool example are the radiation belts. So we saw that we get these, the magnetic field has the shape of a dumbbell. And so that creates a field that is weaker on the edges and stronger at the center. So this has a tendency to kind of trap the charged particles into the field, kind of like a magnetic bottle. And what ends up happening is that we have all these charged particles that are trapped in these radiation belts. And when we get like the solar wind, or the sun goes through like a coronal mass ejection, and we get like a bunch of charged particles that come through, and we get extra charged particles in, if the magnetic field is particularly active and the solar wind is particularly active, as your charged particles get closer to the stronger magnetic fields, that gets them excited. So as they get excited as they're in those fields, and then we know that when electrons jump up in their orbitals, when they come back down, they emit light. And so that's where our aurora come from. So the aurora borealis in the northern hemisphere and the aurora australis in the southern hemisphere are caused because those charged particles get trapped in Earth's non-uniform magnetic field, get excited, emit radiation, and we get to see beautiful colors at the poles. So here's an example. We have a proton that is moving in a circular path perpendicular to a constant magnetic field, and it takes 1.00 microseconds to complete one revolution. And we want to determine the magnitude of the magnetic field. So in this case, the only thing we're given is going to be the period, but we're using a proton, so we can look up the mass, we can look up the charge of the proton. So we do actually know the mass of the proton is 1.67 times 10 to the negative 27th kilograms. We know the charge of a proton is 1.6 times 10 to the negative 19 coulombs on your formula sheet. And we're given that our period is 1.00 microseconds. That's times time to the negative 6 seconds for our period. And we want to determine the magnitude of the magnetic field. So I do want to remember that because we are moving in a perfect circle, and we're having a radius here, the speed is distance over time. Our distance is the circumference, 2 pi r. Our time is the period. So with this equation, we can find the speed at which the charged particle is moving. We also know that our magnetic force is equal to our centripetal force. Our magnetic force is QVB. Our centripetal force is MAC. So QVB is equal to mv squared over r. So our V cancels out on the left, and one of them cancels out here, so we get QB is equal to mv over r. We are looking for the magnitude of the magnetic field, so I need to divide here by Q on both sides. So that is going to give me that B is equal to mv over q times r. So I have this ratio here, v over r. I can rewrite this as m over q times v over r. I'm not given the radius of the circle, so I actually have two unknowns, but I have the same two unknowns here. So if I divide by r on both sides, I get v over r is equal to 2 pi over the period. So I can take that and sub in here. So I get b is equal to m over q times 2 pi over t. So 2 pi times m, which is 1.6 times 10 to the negative 27th kilograms, divided by my q, which is 1.6 times 10 to the negative 19 coulombs, times my period, which is 1.00 times 10 to the negative 6 seconds. We will get a magnetic field. Sorry, that should be 1.67 times 10 to the negative 27th. Sorry. I get a magnetic field that is equal to 0.0656 Teslas. So that'd be a pretty strong magnetic field. So that's just another example of how you can solve problems using kind of this circular motion. Another application is the velocity selector. So this is often used in research because our electrons are moving around randomly in all directions. If you think about it, your atoms, your charged particles, everything is moving around randomly. When chemistry, you talked about like kinetic molecular theory, the idea that every particle in every atom is actually moving around, vibrating, and all sorts of things. We talked about gas laws. Kinetic molecular theory applies best to gases, but even solids, every particle is vibrating. Every electron that is moving all around the electron cloud. So these electrons are constantly in motion. they are all going at random speeds because they're going to get closer to a positive charge and speed up. They're going to get bounced and reflected away by a negative charge. There's all sorts of forces that are acting on them at any one instant. So there might be, based on a temperature, moving on average at a particular speed. That's one of the things that our gas laws teach us, is that the higher the temperature, the higher the kinetic energy of our particles and the faster they're moving. But still, within a material, some electrons are moving slower and some are moving faster. So if I want to do research on charged particles, I want to know that the charged particles I'm doing research on are moving at a particular velocity. So some really clever people designed a really simple device to make sure that only electrons of a particular velocity can get through. So velocity selectors are going to be a combination of electric and magnetic fields. So you're going to have some sort of source of charged particles. A lot of times they use some sort of ionizing radiation, or they use some other form of particle accelerators to kind of collide atoms together and stuff to create differently charged particles. But ionizing is really easy because you just excite them, an electron escapes, and now you have this positive charge. So what you have is, in this case, you have two charged plates. So you have a positive plate here and a negative plate here. They're creating an electric field that is uniform, as long as we kind of ignore the edges and make sure that it's really, really long, that goes from positive to negative. There is also a uniform magnetic field. That magnetic field here is into the page. So what happens is your charged particle enters this field and is going to experience forces created by each. So when we look at this, the electric field is creating a force. We have to recall from our previous unit that our electric force is equal to Q times E. Our electric field is a vector that goes from positive to negative for the charges, but Q is our charged particle that is moving in that field. And remember, we assume that our Q is positive unless, or in this case, our Q is positive. So that means that our electric field and our electric force are in the same direction. If it was a negative charge, then they would be in opposite directions. So since our electric field is moving to the left, our charged particle moving with our velocity is going to have to feel an electric force to the left. So our electric force is going to point towards the left. The stronger the charge, the bigger the charge, or the bigger the electric field, the bigger that force is going to be. At the same time, we have a magnetic force. So our magnetic field is going into the page. And with that, we would use our QVB. So our magnetic force is equal to QV cross B. The magnitude is going to be QVB because our magnetic field B is into the page, our velocity is towards the bottom. Those are perpendicular to each other. But we use our cross product for the direction. So because we're dealing with a positive charge, our fingers would be on our right hand, would point them in the direction of velocity, which is towards the bottom of the page. So I point my fingers towards the bottom of the page. And then I rotate my palm so it's facing the magnetic field, which is into the page. So that points my fingers towards the bottom. My palm is into the page. That's going to force my thumb is going to move to the right. So that means I'm going to experience a magnetic force to the right, which is in the opposite direction of our magnetic field. Now, our electric field is not based on the speed of the particle, but our magnetic field is. So based on the field strengths that are provided, there is going to be exactly one velocity that allows those two forces to be exactly equal to each other. So if we set our electric force equal to our magnetic force, our electric force is Q times E, our magnetic force is QVB. The charge itself is actually going to cancel out, which is kind of cool. So it doesn't matter if we have a single charge or a double charge or we have a huge charge. The charge itself doesn't matter. So it doesn't matter whether it's positive or negative in this case. If it was negative, the forces would be in opposite directions, but they would still need to be equal to each other. So we get that E is equal to V times B. So if we solve for V, V is equal to E divided by B. So all you have to know is your electric field strength and your magnetic field strength, and the velocity of the particle that goes straight through is going to have a magnitude equal to E over B. So what happens if it doesn't have that speed? Well, if it's going too slow, then your FB is going to be too small, which means your electric force is going to take over and it's going to hit the plate. It's going to curve and hit the plate. If your particle is going too fast, your FB is too big, so your rightward force is going to be bigger and it's going to hit the positive plate. So only the charged particles that go through are going to be undeflected. And they're going to make this long enough so that the charged particles will have curved before they ever reach the exit. So only the particles with the perfect velocity are going to make it out of the velocity selector. Another really cool example of an application is the mass spectrometer. A mass spectrometer is often paired with a velocity selector, so that way we know the velocities going into the mass spectrometer. But mass spectrometers are used in things like chemistry to identify unknown materials by identifying the mass of individual atoms in the particles. So in this mass spectrometer, we have a source of our charged particles. There is also a delta V, that is a voltage source. So in this case, what we have is going between here, our source, and here, our wall, you have a potential difference, delta V. So your charged particles are going to leave the source with a speed equal to 0. And they're going to be passed through a potential difference delta V so that they are reaching some sort of speed here at the end. This is one way to do it. So you will accelerate them with a delta V, because that delta V is our change in potential energy. Because remember that change in potential energy is our Q0 times our delta V. And then because we have conservative, the electric field and things are conservative, then that is also going to be the same as negative the change in kinetic energy. So whatever potential energy is lost is going to be gained in kinetic energy. So you're going to get particles that are entering that field. Instead of doing this, you could do a velocity selector. Either way, we need a way to know what speed our particles are moving to go in. Or if we don't know what the speed of our particles are, we could use the fact that we're going to get a curving motion out of this. Because once we have our particles up to speed, whether it's accelerating it through a potential difference or moving through a velocity selector, these charged particles are going to enter this field with a velocity. This is a magnetic field, so your mass spectrometer has this uniform magnetic field in that has a strength of B. Because this is a positive charge, if my velocity is to the right and my magnetic field's out of the page, I'd put my fingers to the right, my palm would be out of the page. That's going to point my thumb towards the inside, towards the right, which is bottom of the page, inside, right. So that's going to create a circular motion, and your particle is going to hit the screen at some distance x here. That is actually the diameter of the circle at that point. And so we could actually use that information in order to find the mass. So we could find the speed. If we know the speed going in, we can use the fact that our R is equal to mv over qb. If you know your charge, you know your speed, and you know the magnetic field strength, our R is going to be x divided by 2. So you can use the distance that it hits on the screen, the known velocity, either because you've accelerated it through a potential difference or you've used a velocity selector to find that velocity, your charge, And if you're doing an ionizing, you ionize it until it's emitted 1 electron. So it's usually just a positive 1 charge. And then you can actually find the mass of your particles using that information. So mass spectrometers are kind of cool. I have some additional videos of problem solving examples for mass spectrometers that I have linked in there from other people that'll help you if you have any homework questions like that.